We're going to be doing 062542 May June 2021 paper today. Question number 1. Figure 1.1 shows a sealed weather balloon which is stationary in still air. You should highlight this or underline this while reading the question. State whether the overall density of the balloon and its instruments is greater than, less than, or same as the density of the surrounding. In the question it says that it is stationary, which means that the density of the weather balloon and the surrounding air is same. For example, if the density of the balloon was more than the density of the surrounding air, the balloon would go down. And if the density of the balloon was less, the balloon would go up. So we can write down here it has same as the density of the surrounding. Part B says at night the gas inside the balloon cools down. The pressure of the air outside the balloon remains same. Part I says state whether the balloon rises, falls, or remains stationary. As I told you, if the density of the balloon increases, the balloon is gonna go down. So we can write down here it falls. Part 2 says explain your answer. Well, the reason behind this is that as the gas inside the balloon cools down, the volume decreases, right? And density is inversely proportional to volume. Therefore, the density increases. And as the density increases, the balloon falls down. We can write down that here. As the gas inside the balloon cools down, the volume decreases. Density is inversely proportional to the volume. Therefore, the density increases. So as the volume decreases, density increases. Now, as the density increases, the balloon is going to go down. Part C says an object is released from the balloon. It starts at rest and eventually reaches a constant speed. You should highlight this when you're reading the question. It starts at rest, which means it's going to start from, the graph is going to start from origin and eventually reaches a constant speed. This means that the gradient at the end will be 0. As I am using a digital copy, I don't have any access to pen, so I'm going to be giving you an example here. This is exact example. You have to draw a graph like this. The graph starts from origin and here the velocity is constant. So that's why the gradient is 0. Part 2 says state the values of the initial acceleration and final acceleration of the object. As you know that when a person is holding an object, for example, in this case, a stone, the force acting on the stone is gonna be the acceleration, the gravity, the pull of the gravity, which is 9.81. So we can write here initial acceleration is 9.81 meters per second square, as the gravity is pulling that stone down. Final acceleration is gonna be 0 because you can see here that the gradient is 0 and velocity time graph, the gradient of velocity time graph gives us acceleration. So we can write here 0 meters per second square. Question number 2, part A. Define the moment of a force. The definition of moment is force into perpendicular distance of the pivot. Force into perpendicular distance of the pivot. Part B says figure 2.1 shows an object of negligible weight. The object is in equilibrium. The object is free to rotate about its point B. So this is the pivot and this is the perpendicular distance given to us, 12 centimeter and 20 centimeter. We have mass here, which is 50 kilograms. Calculate the value of the force F. So here you can see that we are given with F1, which we have to find F1, which is this force. And the distance is 0.12 meters. Convert this into meters. Force 2 is given, which is 50 into 10 because this is mass and you have to convert this into force, which is going to be acceleration. 50 into 10, which is the gravitational constant, 10. Distance, which is 0.20 meters. You have to convert this into meters. which is gonna give us 0.20 meters. The object is free to rotate about its point P. Calculate the force F. We can use our F1 D1 equals F2 D2 formula here, and we know D1, we know F2, and we know D2. So we can plug in our values here, which is gonna give us 500 into 0.2, which is F2 into D2 equals F1 into 0.12, which is distance here. And we are going to rearrange our formula and get our force, which is going to be 833. And if we round it off, we're going to get our answer as 830 newtons. Part C says, describe an experiment involving vertical forces to show that there is no net moment on an object in equilibrium. You may draw a diagram in the space provided. When they say you may draw a diagram, you have to draw a diagram. Okay, even if you miss a point, they're gonna look at your diagram and give you the marks for that. So this is the diagram which I chose. This is the pivot, and the distance between these both is 30 centimeter. Mass 1 is 20 centimeter apart from the pivot, and mass 2 is 10 centimeter apart from the pivot. Both are in equilibrium, and mass 1 has a mass of 5, it's not mass, a weight of 5 Newton, and mass 2 has a weight of 10 Newton. So what do we have to do is find the clockwise moment. What is gonna be clockwise moment? This mass 2 is clockwise, so we're gonna find the clockwise moment, which is gonna be 10 into 10. The formula for moment is force into perpendicular distance. So here is force, which is 10 Newton, and perpendicular distance is 10 centimeter, so which is gonna be 100. Now to calculate anti-clockwise moment, which is gonna be 20 into 5, because the perpendicular distance is 20 centimeter and the weight is 5, which is gonna give us 100. So what can we conclude here? We can conclude that total anti-clockwise moment is equal to clockwise moment. Therefore, we don't have any moment. Question number 3. Figure 3.1 shows water flowing at very slow speed over a cliff edge. The water falls 15 meters onto the rock below. Show that the velocity of the water when it strikes the rock is 17 meters per second. And the only information we are given in this question is the height, which is 15 meters. How do we calculate velocity from a given height? Well, as we know, if an object is falling from up, its potential energy will decrease and kinetic energy will increase. And if the object is going up, the potential energy increases and the kinetic energy decreases. So in this case, we can use the formula loss in potential energy equals gain in kinetic energy. What is potential energy? Potential energy is mgh, and kinetic energy is half mv square. And now we can cancel the mass. So we have gravitational constant, which is 10, and height is given, which is 15 meters. And we need to find velocity. So we plug in our values. We have 10 into 15 equals half v square. Now we can bring the 2 on this side and square root the whole answer, which is gonna give us square root 300, which is gonna be 17.32, which is approximately 17 meters per second. Part B says 30 kilogram of water flows over the cliff edge every second. Calculate the force exerted on the rocks of the falling water, ignoring any splashes. So what is given in this question? We're given with the mass. We calculated the speed, which is 17.32 meters per second, and the height is given, which is 15 meters. So we can use the formula F equals mv, force equals mass into velocity. We're given with the mass, which is 30 kilograms, and the velocity we just calculated, which is 17.32 meters per second. And we get our answer as 519.6, which if we round off, we get 520 newtons. Question number 4. Pollen particles are mixed into a liquid. They are seen to move when observed through a microscope. Describe this movement. As they don't have any particular path, they will have a random motion. So we can write here random motion. They hit each other and change their path. Explain this movement in terms of molecules of the liquid and the pollen particles. The liquid molecules and pollen particles move and collide with each other. Okay, you can write here. They gain kinetic energy and move faster. After that, what happens is the collisions from different directions cause random motion. So when liquid molecules and pollen particles move and collide with each other, they gain kinetic energy and move faster. Therefore, what happens? Collisions from different directions cause random motion. Part B. Medical professionals sometimes rub ethanol over the skin of a patient. Ethanol evaporates readily at room temperature and has a high specific latent heat of evaporation. State whether the patient experiences heat, cooling, or neither at the site where the ethanol is applied. Explain your answer. So when you apply ethanol on the part of the skin, what happens? The thermal energy is required to evaporate ethanol. Here you can see in the question they say that ethanol evaporates readily at room temperature. That means it gains thermal energy and it evaporates. The thermal energy is taken from the side of that skin. From that side of the skin. Molecules with high energy will leave the surface. So we can write here, we can give a statement that it cools down. Why does it cool down? The thermal energy is required to evaporate ethanol. As they said in the question, it evaporates. Okay. And then the thermal energy is taken from the side of that skin. Molecules with high energy will leave the surface because they gain enough kinetic energy that they can break the bonds and escape into the atmosphere. Part 2 says, state any effect on the rate of evaporation of ethanol when a fan blows air over the patient's skin. When the fan blows air over the skin, the molecules gain kinetic energy, and the molecules with more kinetic energy will leave the surface. As the fan is providing kinetic energy to them, the rate of evaporation increases. So we can write down here increases. Question number 5a. A machine delivers a hot drink in a plastic cup, which is uncomfortably hot to hold. Figure 5.1 shows the cup with the hot drink. Okay, this is the hot drink and this is the plastic cup. Figure 5.2a shows the cup with the hot drink and the holder for the side of the cups. Figure 5.2 shows cross section through the holder. The holder is made from two strong paper cylinders separated by a waxy piece of strong paper to make air gaps. Explain how using the holder makes it comfortable to holding the cup. The holders have air in between them, and air is poor conductor of heat. So holder reduces the conduction of thermal energy, and the temperature outside the holder is lower, making it comfortable to hold. So we can write it here that holder reduces conduction of thermal energy. That means the energy from here, thermal energy from here, won't be transferred here. and it will be more comfortable to hold them. Air is poor conductor of heat. As air is poor conductor of heat, it won't let the thermal energy get transferred from inside the cup to the holder. And what happens? The temperature of outside of the holder is lower, making it comfortable to hold. Part B says a student carries out experiments on the cooling of the hot drink described in A with and without the holder in place. He finds that the holder only reduces the rate of cooling slightly. Suggest and explain another action that reduces the rate of cooling more effectively. So we can write here, add lid on the cup. When the lid is there on the cup, there will be no evaporation from the surface of the container, thus reducing the rate of cooling. When you put a cover on this, what will happen? The molecules won't go out of the cup. They will stay inside the cup. That's why the rate of cooling will be reduced. Part C says state any method of thermal energy transfer from a star through the vacuum of the space. And you can see there are three types of energy transfer, which is conduction, convection, and radiation. Conduction and convection cannot take place without a medium. So our answer will be radiation. Question number 6a. Figure 6.1 shows a ray of green light passing through a prism. So here's the ray of green light which is passing through a prism. A ray of blue light is directed towards the prism on the same path as the ray of green light. On figure 6.1, draw the path of the blue light through and out of the prism. I have given an example here. As we go down through the spectrum, the lines will get away from the normal. Okay, this is the rule and you have to learn this. You might have to learn the names as well for light spectrum. And the rule is whenever you go down through the spectrum, the lines are gonna get away from the normal. So here we can draw a ray of light which is gonna be blue. It takes the same path as the green light. However, it's gonna be away from the normal. And the line is going here. Of course, in exam, you have to draw with one pencil or pen. So you don't need to add the colors and all. You just need to add arrows and make sure the light ray is away from the normal, because in the light spectrum, it goes down. As you can see here, red is more towards the normal as compared to violet. So we can conclude that as you go down through the light spectrum, the rays get away from the normal. So the wave of the blue light in air is 4.8 into 10 raised to power minus 7 meters. Calculate the frequency of the blue light. The wave of the blue light in air is 4.8 into 10 raised to power minus 7 meters. Calculate the frequency of the blue light. What is given in the question? We're given with the wavelength, which is 4.8 into 10 raised to power minus 7. And the velocity, we know speed of light, which is 3.0 into 10 raised to power 8. And we have to find the frequency. What is the formula for frequency? V equals F lambda. And we can rearrange our formula and find F, which is going to be V by lambda. Our V is 3.0 into 10 raised to power 8 and divided by the lambda, which is given in the question, 4.8 into 10 raised to power minus 7 meters. So we get our frequency as 6.25 into 10 raised to power 14. We can round that off and write it as 6.3 into 10 raised to power 14 hertz. Don't miss the units. Question number 7a. Figure 7.1 shows two magnets and the gap between the North Pole and the south pole of other magnet. On figure 7.1, draw three lines to show that the pattern and the direction of magnetic field in the gap. The magnetic field, the lines are already drawn, and you know that magnetic field is represented like this, and this is not given in the question. So we are done with this part, and don't forget to add the arrows, which is going to be from north to south, and you get 1 mark for the field lines and 1 mark for the arrow. Question number 7, B part. Figure 7.2 is a repeat of figure 7.1, showing two magnets. On figure 7.2, draw the position of a plotting compass needle when it comes to rest in the gap between the north and the south pole. So what is a compass? I have an example here, which is this is a compass. It has north and south poles, and this is the needle, right? And the needle is always going to be pointing towards the north. This is uncalibrated, so it's not pointing the north. So we can draw this same compass between the magnets, which is going to be this, and it's going to be pointing the north, and the north part of the compass should be facing towards the south, and the south part of the compass should be facing the north part of the magnet. And you get 1 mark for this. Explain why the needle comes to the rest in this position. So the needle points towards the direction of the magnetic field line, and the north pole of this compass points towards the south pole of the magnet. So that's why it comes to rest in this position. Describe a method of demagnetizing a bar. There are many methods. I have given some examples here. The first one is heating, the second one is hammering, and the third one is electrical method using alternating current. So in this example, I'm going to be writing heating or hammering with the magnet lying magnetically east to west. So you get 1 mark for heating or hammering, and you should write magnet should be lying magnetically east to west. We're done with this question. Question number 8. Part A. Two identical radioactive sources emit alpha particle and gamma rays into two vacuum tubes. Figure 8.1 shows two electrically charged particles on either side of one of the vacuum tubes. So this is positive and this is negatively charged. Initial path of beam of alpha particle and gamma rays. Write the symbol alpha once in the table 8.1 to indicate any deflection of alpha particle. Write the symbol gamma once in the table 8.1 to indicate any deflection of gamma rays. We know that gamma rays have no charge, so they are unaffected by magnetic and electric fields. And alpha particles are highly ionizing because of their double positive charge. And beta particles are small and fast moving particles with negative electrical charge. As you can see here, when we fire alpha particle, as it is positive, it's gonna deflect downwards. So it's gonna be downwards of the bottom of the page, which is gonna be here. The path it's gonna take is like this. And the second is gamma particle. It's not gonna get affected because it does not have any charge. So we can write here gamma here when in the section of no deflection, and alpha and towards bottom of page, and you get 2 marks for this. Part 2 says figure 8.2 shows the poles of very strong magnets on either side of other vacuum tube, the initial path of alpha particles and gamma rays. So this we can consider as the path of the current, and we have to use Fleming's left hand rule as they have included magnets here. So instead of current, we can use the path of the particles. And here we have our left hand, which is this. And according to this, we have our magnetic field going downwards, and the second finger should be towards the right side. I can't do that here, but when you do it towards the right side, the force is gonna go into the page. Okay, so we can write our answer here, which is gonna be into the page. Alpha particles are gonna go into the page, and gamma particles are not gonna get affected because they don't have any charge. Part B says that figure 8.3 shows a simple direct current, which is DC, electric motor with a split ring commutator. And we can see the diagram here. There are two magnets given, one is north and one is south, and this is the coil. These are the split rings, and these are the brushes, and this is the battery given here. As we can see from the diagram, this is the positive side and this is the negative side. So the current will be flowing on this direction, like this. And the magnetic field will always be from north to south. But ICs state and explain the direction of rotation of the coil as it seems from point X. So I'll draw the diagram here. So I have drawn this diagram and it's pretty simple. Now it's a bit more complex, but then you can see a clear representation of the diagram. Here's the battery, here's the plus minus side, and the current flows from plus to minus, from here till the minus side, to the minus side. And the magnetic field will always be from north to south. So in this part it says state the direction of the rotation. So we're going to take this point, okay, and use our Fleming's left hand rule. So the magnetic field is going towards the right, and we have the current going this way, which is out of the paper, and the force will be up. According, if we use our Fleming's left hand rule, the force is going to be up. See, the magnetic field is towards the right and the current is out of the paper, so the force will be up. And when you change the direction of the current, the force is going to be down. If we take our point our second finger into the paper, the force is going to be downwards, according to Fleming's left hand rule. So we can write down here, it has a clockwise rotation. So if the force is downwards on the right side and upwards to the left side, the rotation is going to be clockwise. Explanation is force on the left side is upwards and force on the right side is downwards. That's why it is clockwise movement. Part 2 says the coil rotates through 90 degrees from its position. State what happens to the moment in this position. What is moment? Moment is force into perpendicular distance. As this moves here and the perpendicular distance is 0, there will be 0 moment. So we can write here 0 moment. Part 3 says the coil is rotated through 180 from the position shown. By considering the force on the coil, explain how the split ring commutator enables the motor to turn continuously. When this rotates 180, the direction of the current should be changed, because on this side the direction is going out of the page, right? And when this will move here on this side, the direction of the current should be changed and it should be into the paper. So we can say that it helps us by changing the direction of the current. So the forces on the wire changes. As this side of wire will come here, the force will be, instead of upwards, it will be downwards. The same thing applies for the right side. The forces on the wire changes, upwards on the left and downwards on the right. Question number 9, part A. Figure 9.1 shows a circuit. This is a DC motor and this is ammeter, and this is a battery given here. On figure 9.1, draw two clearly labeled arrows to show the direction of the electron flow and the direction of the current, conventional current in the circuit. As we know, the flow of electron is from negative to positive. So we can draw the flow of electron, which is going to be from negative to positive side. And the conventional current is always opposite of the electron flow. So the conventional current direction will be this. Part B says the current in the motor is 13 ampere. The charge on an electron is 1.6 into 10 raised to the power minus 19 coulombs. Calculate the number of electrons that pass through the motor every second. So the information we are given with is the current is 13 ampere. The charge is 1.3 into 10 raised to the power minus 19, and the time is 1 second. So what equation relates this? The only equation which relates this is Q equals IT. This is electron charge. Remember this is electron charge. So we have to find the charge on motor. So to find the charge on motor, we have to use this equation, which is Q equals IT. We are given that the current is 13 ampere and the time is 1. So we get the charge as 13 coulombs. Now the number of electrons is equal to charge of motor, which we have calculated here, Q, divided by the charge of 1 electron. What is number of electrons? The number of electrons is Q divided by charge on 1 electron. So Q equals Q divided by charge equals number of electrons, and then we can see 13 divided by 1.6 into 10 raised to the power minus 19 will give us numbers of electrons. We can do that here and we get our answer as 8.12 into 10 raised to the power minus 19, which we can round off and write it as 8.1 into 10 raised to the power minus 19. And we're done with this part of the question. Question number 10. Figure 10.1 shows the potential difference, which is current graph, potential difference and current graph for a circuit component K. This is potential difference and this is current and this is milliampere. Calculate the resistance of the component K when the current is 4.0 milliampere. So we can draw our line here and find the potential difference at 4.0 milliampere, which is gonna be 9.2, around 9.2. This is an easy way to find the values from the graph, which I use for these type of questions. You can take out your calculator and you can see here 2.0 takes 5, right? So we can write 2.0 divided by 5, which means 2.0 takes 5. And now we need to find what is this, right? So 5, 10, 15, 20, 23. So we multiply by 23 and we get our answer as 9.2. See, so we have the value of potential difference, which is 9.2, and we have the current 4.0 milliampere now. So we can use our formula V equals IR. We know the potential difference and the current now. So rearranging the formula, we will get R equals V by I. The value of V is 9.2 and the value of current is 4.0 into 10 raised to the power minus 3, because you have to convert from milliampere to ampere. And then R equals 2300, which is going to be 9.2 divided by 4.0 into 10 raised to the power minus 3. And we write 3 here, minus 3, which is going to give us 2300. And don't forget to add the units here for resistance. So we can write here 2300 ohms. We're done with this part. Part B says figure 10.2 shows a circuit containing component K, and this component is thermistor. At lower temperature, component K has much greater resistance than resistor R. At high temperature, component K has much smaller resistance than resistor R. State and explain the effect on the lamp when the temperature changes from very low to very high. Refer to the voltage at point X in your explanation. So as you know that V equals IR, and I is inversely proportional to R. As R increases, I decreases. Okay, and in the question it says at lower temperature the resistance is high, and at high temperature the resistance is low. So that means the resistance is less now. Okay, and when the resistance is less, the current increases, and when the current increases, the lamp will turn on. So we can write down here the statement will be much greater current passes through component K, and the explanation we can write is resistance of component K decreases, so the voltage across point X decreases. Therefore, larger current in the lamp, which will light up the bulb or lamp. We're done with this part. Part C says state the name of component K, and as I told you before, this is a thermistor. For this you have to learn all the components of the circuits, and it's better to memorize them so that you're familiar with all the basic components in the circuit. So we can write here thermistor. Question number 11, and which is the last question of this paper. A part says a student investigates a radioactive substance in a laboratory. Figure 11.1 is a graph showing the count rate detected as the substance decays for 7.5 minutes. The background radiation is 20 counts per minute. Part 1 says determine the half-life of the substance. So to find the half-life of the substance, you have to find the count rate at t equals 0, which is 220, and minus the background radiation, which is gonna give us initial count rate without the background radiation. So initial count rate without the background radiation is gonna be 220, which is from here t equals 0, the graph is touching on 220. And minus the background radiation which is given in the question, so we get 200. Now the count rate of the substance after one half-life, which is going to be 200 divided by 2, which is 100. Now the total count rate after one half-life is going to be this count rate plus the background radiation, which is going to be plus 20. So which is going to give us 120 here. And we can find out where does the graph touch at 120. So here we have 120, and this is the point where the graph touches us. So if 1.0 takes 5, then how much does 12 take? It's 2.4. So our answer is gonna be 2.4 minutes. Of course, don't forget the units. Part 2 says calculate the count rate detected at time t equals 9.6. So what things are given in the question? First of all, we're given with half-lives, which is 9.6 minutes. And we are given with the time of one half-life. So we're gonna find out how many half-lives are there, number of half-lives, which is gonna be 9.6 divided by 2.4, which will give us 4. And we have to find the count rate. The initial count rate while starting is 200, not 220 because we have subtracted the background radiation. So it's going to be 200 into the half-lives, which is going to be half 4 times, and which is going to give us 12.5. This is our new count rate after 4 half-lives. And now don't forget to add the background radiation, which is going to be 15 plus 12.5 plus 20, which is going to be 32.5. And if we round this off, we're going to get 33 counts per minute. Part B says the substance emits alpha particles and gamma rays. The student suggests that it's safe to store the substance in plastic container of thickness 2 millimeter. State and explain whether the student's suggestion is correct. I have given a diagram here which shows that alpha particle is the least ionizing, and it just needs a sheet of paper, and beta particle only needs aluminum sheet or something, and gamma particles need something made out of lead. So we can conclude here that the student is not correct, and gamma ray is harmful and cannot be stopped by plastic containers. The student must use lead container, as it stops the gamma rays from passing through the container. And this will be our answer for part B. We are done with the paper, and I hope you understood everything. If you have any questions, comment down below in the comment section. I'll try to respond as soon as possible. Like, share, and subscribe this channel, and see you in the next video.